Hi, my name is Sandeep Kumar. I'm a PhD student at IIT Delhi, India. Today, I'll be talking about our paper that is SecureFS, a secure file system for Intel SGX. Here is an outline of my talk. I will start with a brief introduction of Intel SGX and we will discuss its capabilities and its limitations. We will also discuss why a secure file system is an issue here. Then I will define our problem statement, followed by a glance at what has been done by the prior work to eliminate this issue and how they fall short. After that, I will discuss a high-level solution design of our work, focusing on how it differs from prior work in this area. Finally, I will conclude with some evaluation visuals. Let us get started with the introduction. What is Intel Secure Guard Extension, or SGX? Intel SGX is a trusted execution environment offering from Intel. Its main objective is to securely execute an application on a remote untrusted system. By security, we mean that the confidentiality and integrity of the code and the data are maintained. The security is guaranteed even in the presence of a malicious user with a root level access. SGX also guarantees the security even if the operating system or the hypervisor is compromised. Here, the CPU is considered to be secure, along with a portion of the main memory. The data present on the reserved main memory is encrypted and is managed by the hardware. The data is only decrypted on the chip. To summarize, SGX provides a secure way to execute an application. The data is always present in an encrypted form and hence free from any kind of snooping or tampering. Furthermore, all these properties are guaranteed by the hardware. Now we will discuss some of the limitations of SGX. First, the amount of secure memory available to SGX is limited to 128 megabytes, out of which only 92 megabytes is usable. The data here is managed by the hardware, and although the OS can read it, it cannot decrypt it. Any tampering here is also detected by the SGX hardware. The limited amount of memory creates challenge for applications using a memory more than 92 megabytes. SGX handles such scenario by transparently evicting pages from the secure region to the unsecure region and loading it back whenever there is a fault on it. However, this is the costly process and should be avoided by limiting the memory usage. Furthermore, as already discussed, the operating system is not a part of the trusted component of SGX. This allows SGX to maintain security guarantees even in the presence of a malicious operating system. However, this puts few restrictions on any applications running with SGX, most notably being no access to the system calls, as it requires trusting the OS. Consequently, application within the SGX cannot access the file system. Please note that there is an indirect way to access the file system. However, that requires significant application code change. We will discuss that while discussing the related work. We will now discuss our problem statement. Our aim in this work is to bring the storage within the scope of SGX guarantees. An application running within SGX should be able to access the file system securely, efficiently, and without any source code changes. We will see in the subsequent slides that the existing work in this area is slow and is vulnerable to replay attacks that violates the freshness property of the file system. Hence, our goal is to develop a fast and secure file system that is immune to replay attacks. Now, we will discuss some of the prior work in this area. Primarily, there are three designs for a secure file system. The first one is an encrypted file system using the untrusted host file system. Here, the data is to be stored on the file system is first encrypted. This approach guarantees confidentiality. However, it incurs significant performance overhead due to an encryption operation every time we write data and a decryption operation every time we read data. The second option is an in-memory file system. Here, the complete file system is maintained in the secure region of the main memory, the area reserved by the SGX. This design offers the highest level of performance and security. However, as the amount of reserved memory is limited, the total capacity of such a file system is also limited. The third option is to use a hybrid design. Here, the set of hot data is kept in a secured memory. However, as the file system grows, a portion of the data is offloaded to the untrusted file system after encrypting it and putting integrity checks in place. Our solution is based on this design. Here, we will discuss what actually happens when the data is flushed from the secure SGX memory to the untrusted host file system. The first step is to split a file, F in this case, into fixed size chunks. The file system works at the granularity of these chunks. We have used a 4 KB size for these chunks. Now, let us suppose the chunk F1 is to be written to the disk. The first step is to hash the data, then generate a key at random, encrypt the concatenated version of the data and its hash using the generated key. The key is stored in the metadata structure and will be used to decrypt the data later on. The encrypted data is sent to the untrusted storage. The encryption guarantees the confidentiality, the hash guarantees integrity, and generating a new key every time ensures the freshness of the data. This technique is used by PriorWork and by us also. We will now see a replay attack on the design of current systems. Here, a secure file system volume consists of the data and the metadata in encrypted form. A user can mount the volume by providing the volume key. Let us suppose the user mounts the volume, changes the state of the volume to F, and unmounts the volume. Here, the volume key is used to decrypt the data and metadata while mounting, and let encrypt it while unmounting. Subsequently, the user mounts the volume again and changes the state from F to F dash and unmounts. In a replay attack, an attacker can just replay the old encrypted blocks of the file system. The file system has no way of figuring out that this is old data. The hash dependency between the data and the metadata is still valid. We were able to mount this attack on all the PriorWork. Apart from this security issue, there's a performance issue also. Modern file systems use an inode structure, as shown in the figure. If the size of a file is small, the data blocks can be directly accessed using the direct blocks. However, as the file size grows, single indirect blocks, then double indirect blocks, and eventually even triple indirect blocks are engaged. Here, the leaf node contains the data and the inner nodes contain the metadata of the blocks pointed to by them. This structure provides an efficient way to access data in a normal file system. However, this tree structure creates a problem in case of a secure file system. As seen previously, the randomly generated key is stored in the metadata. This tree-like structure creates a dependency. If a data block is flushed to a disk, the key is stored in its parent, essentially changing it. This will require a key update to the parent of the parents, creating a cascading effect till the root, that is inode. Hence, in the worst case, a single write operation is converted to 3 additional write operations. We call these updates as cascaded updates. Finally, there's a compatibility issue. Intel SGX provides a trusted library called the Intel Protected File System that can be used to store data on the untrusted file system. Apart from the earlier mentioned replay attack, using the IPFS, using the Intel Protected File System also requires a source code change, as the name of the function for doing the file system operations are different. To summarize, the existing work in this domain is vulnerable to replay attacks. This attacks violates the freshness property of a file system. This is a non-trivial problem to solve, as SGX semantics does not cover the freshness of data in rest. The second point is that and inode-based metadata management is well suited for modern-day file systems. However, they're ill-suited for a secure file system. Hence, we need a better metadata management system. And finally, the design of the file system should be compatible with the existing applications without any source code modifications. We will now discuss the design of SecureFS. We start with the understanding what is actually required from a secure file system for SGX. We start by characterizing the file system access pattern of the most commonly used workloads by the community in this domain. The workloads are from different domains such as databases, machine learning, license managers, blockchain, and web services. We mainly focus on the access pattern of these workloads, the size of each accesses, amount of data read and write operations, and what percentage of a file is accessed. Here is the typical pattern of most of the applications. Most of the workloads used with SGX are compute intensive. A typical pattern is that the application will read some data in the beginning, such as the genesis block for a blockchain or the input data to a machine learning application. The data is read in a sequential manner. In this plot, we have time on x-axis, and the y-axis shows the difference between the end of the read or write request and the starting location of the next read or write request. A value of 0 indicates that the current operation starts at a location where the previous ends, a sequential operation, which means there was no seek between two requests. Once the data is read, there is very little or no interaction with the file system. Thus, this state is dominated by the CPU-intensive operations. Once the application is done with its processing, it writes the results of the calculation back to the disk. Apart from this, we also see a random data access pattern in the application that deals with encrypted data, such as license managers. However, these are limited to only crypto-related applications. Most of the applications show a sequential access pattern. Using the characterization results, we will now discuss how we optimize the metadata storage of the file system. The basic idea is to eliminate the cascade writes for a single write operation. Turns out we do not have to look far. A file allocation table or FAT-based file system is ideal for such scenarios. In a FAT-based file system, the storage area is divided into fixed size blocks. A table called a FAT table has an entry corresponding to all the blocks in the file system. The blocks of a file need not be allocated contiguously. It can be spread out across the FAT table and is located using the pointers present in the FAT table entries. A FAT table provides a single location to store all the metadata for all the blocks. In the case of sequential access, the data can be easily accessed by following the pointers, which we just saw is indeed the case. Most of the application access data sequentially. Hence, we use a FAT-based file system for SecureFS. We modify the table to store the keys of the blocks. We'll discuss the performance implications of this while discussing the performance of SecureFS. We now discuss how we solve the issue of replay attacks on the secure file system. The data and the metadata is present in an encrypted form on the disk, following the hybrid design. We store a snapshot of the data in plain text in the secure memory. The size of the metadata can also grow to be of significant size as the data in the file system grows. For a 1 GB file system, we need approximately 9 MB of memory. This is 10% of the total secure memory available. Hence, we cannot pin this memory in the secure region. However, we do need a root of trust. To solve this issue and the replay attack, we enable evictions of the portion of metadata to disk. Following the same procedure as data, we divide the metadata into fixed size blocks, which we call slabs. The eviction procedure is same as the data blocks. The keys of the slab is stored in the slab table. In our implementation, the size of a slab table is only 56 kilobytes. As long as the volume is mounted, the slab table is pinned in the secure memory. This acts as our root of trust. Any tampering with the data will be detected by the metadata, and any tampering with the metadata will be detected by the slab table. Now, while unmounting, we must ensure that the attacker cannot replay this data back. Otherwise, she will be able to mount the attack. Intel SGX only guarantees confidentiality and integrity. Freshness is not a part of the semantics. To solve this issue, we introduce a step where during the unmounting of the volume, the hash of the slab table is calculated and sent to a secure remote server. This ensures that during the next mount, there is a key and hash dependency between the slab table and the data. Note that this is only required during the mounting and unmounting of the volume. When the volume is mounted, all the operations are handled by the metadata or the slab table locally on the system. Recently, Intel announced secure monitoring counters. This can also be used to ensure the freshness of the data locally. However, they are limited in terms of how many updates can be done on them. Now, how will this design prevent a replay attack? Going back to our example, we now have a slab table that acts as a root of trust during the mounting of the volume. When state is f dash, there is a second time the hash of the table is obtained from a secure server. And the locally stored slab table is validated. An old version of the slab table will fail the integrity check. Note that Intel SGX provides a secure way to communicate with the remote server. This is called remote registration. However, as this is a costly operation, we limit it to only while mounting and unmounting of the volumes. We will now discuss the evaluation results of SecureFS. We have implemented this on a real SGX-enabled machine. For comparison purposes, we have implemented two versions of SecureFS. One that uses a FAT-based metadata management system, and another that uses inode-based system. The former is called SecureFS FAT, and the latter is called SecureFS inode. The results are for writing and reading 1 GB of data using the iZone file system benchmark. As can be seen, for a write operation, the inode-based file system has a 2 times higher latency than the FAT-based file system. This is due to the cascade effect. The read operation have the same latencies, as there is no update operation and the access is sequential. Next, we integrate our two variants of SecureFS with Graphene SGX. Graphene SGX is a library operating system that supports the execution of unmodified binaries on SGX. It has a protected file mode where the data written on the disk is encrypted. As mentioned before, this design is also vulnerable to replay attacks. We compare the SecureFS performance with the protected files mode of Graphene SGX. In the first case, SecureFS volume is mapped to the secure memory. That is, all the allocation happens from the secure memory. In this case, the performance is comparable. However, as we are only writing encrypted data to the memory, and we have a root of trust pinned in the secure memory, we can map SecureFS volume in the untrusted part of the memory. Doing so eliminates the cost of costly SGX memory management system and improves the performance by 120%. Finally, we compare the performance of SecureFS with Nexus. Nexus ensures the mount and unmount of volume are secure. Once mounted, the data is available to all the applications present in the system. It is stored in plain text in the memory. The data is encrypted back when the volume is unmounted. We configure the SecureFS in a similar way. Here, the file system is still protected as before. However, application running without SGX can also access it. For selected workloads, SecureFS has a nominal overhead of 1.8% while adding to the security guarantees. To conclude, here are the key takeaways from the presentation. Via extensive characterization and how a secure file system handles encryption, we showed that the requirements of a secure file system and traditional file system differ. We further showed that doing encryption is not enough, as it makes design vulnerable to replay attacks. We design a novel file system that is immune to replay attacks, and we use the insights from the characterization to ensure an optimal write operation by simplifying the metadata operation. This results in a nominal performance overhead of 1.8% over the current state of the art, while improving on the security guarantees. With that, I would like to thank the listeners, and we are open to questions. Thank you.